Okay, let's continue with the extreme values subtopic. Okay, if y is given in a closed interval a comma b, then the extreme values may occur at one, the interior points where f prime of x equals 0, okay, and this is critical point, and the second one, okay, the interior points, okay, where f prime x does not exist, that means singular point. And the third one, the endpoints f of a and or f of b, okay, and these are the endpoints, okay, and let me give you a theorem about these critical points. If f has a local maximum or a local minima value at an interior point x equals c, and f is defined at x equals c, then f prime of c equals 0, okay, this is critical point. Okay, let me give you an example to understand this theorem clearly, okay, and if y, which is also f of x, equals to x cubed over 3 minus 3x, okay, for minus 3 comma plus 3 closed interval, okay, and what can we say about these functions, critical points and the singular points, and also endpoints, okay, and let me firstly to define the critical points of that. So del f over del x equals to, we know that which is f prime of course, and it's equal to x square minus 3, and which is f prime equals to 0, And we know that the x equals to minus and plus square root of 3. Okay, this is the critical point. Okay, and the f of square root of 3, okay, it equals to approximately, okay, when you put this value into the function, okay, you will obtain minus 3.46, okay, and which is, we know that it's also minus 2 times square root of 3, okay, and the another critical points value, which is minus square root of 3, it is approximately equals to plus 3.47, 46, and it's equal to 2 times square root of 3. Okay, and we know that its graph, when you sketch this function's graph on the coordinate system, okay, and it will be firstly okay, and this point is plus 3, this point is minus 3, this is minus square root of 3, and this is plus square root of 3, and this function is f of x equals to, okay, x cubed over 3 minus 3x, okay, and let's talk about the endpoints of this function, and which are minus 3 and plus 3, of course, and so what can we say about that? That's and the endpoint of the function f of minus 3, it equals to 0, and the f of plus 3, it equals to 0. Okay, and don't forget the previous, okay, definition, and if f prime of x does not exist in any interior point, so we can say yes, that point is singular point, and we know that this polynomial function, okay, has derivation in the whole of the domain of this function, okay, and so it can be derivated, okay, so we can say no singular point here, okay, endpoint, and no singular point. Okay. And continue with another example. If f of x equals 1 minus absolute x, okay, for the domain x elements of the minus 1 comma plus 1, okay, close interval. So this is a piecewise function, and you can extract this function by 1 minus x when for, okay, interior of absolute, which is x, okay, is larger than or equal to 0, and the 1 plus x where for x is less than 0. Okay, and what can we say about it? And let's talk about firstly critical point of this function, okay, and what can we say? And we can say del f over del x equals to, okay, minus 1, okay, when x is larger than or equal to 0, okay, and again del f over del x equals to this time plus 1, and when we know that when x is less than 0, so we can say for this function, okay, no critical points, okay, and after that we can say, is there any singular point, okay? Yes, we have one singular point, okay, and one singular point which is x equals to 0, okay, and of course when x equals to 0, y equals to 1, okay, because of there is del f over del x, okay, does not exist, okay, and let me sketch this function on coordinate system, okay. This is 1 minus x function. This is 1 plus x function. I'm sorry. This one is 1 minus x and this one is 1 plus x function, okay, and this is minus 1 and this is plus 1, okay, and we don't care, okay, this part of graph, okay, because of the domain of this function is in this closed interval, okay, and so look at it at this point, okay, and at this point we have local minimums, okay, and also absolute minimums, and for this point which is singular point, okay, and the singular point local and absolute maximum 2, okay, and the endpoints are, we said that the local minima and also absolute minima, okay, and let me continue with another example about these critical points, okay. If y equals to square root of 1 minus x squared, okay, and for minus 1 less than or equal to x is less than or equal to plus 1, okay, and let me sketch this function, okay, and we know that this is a half circle, okay, okay, and this part is plus 1 and this part is minus 1, and this is the plus 1 again, and for this function, okay, and del y over del x, okay, equals to 0, okay, and it must be it equals to 0, and we know that the x equals to 0, okay, from this part, so this point is, okay, critical point, okay, and then we know that, and after that for these functions these points are singular point and also endpoints. Okay, and this critical point is local or absolute maximum, and these points are local or absolute minimums. Okay, please think about why on these points. Okay, we don't have any derivation. Okay, please think about that. Okay, because we said that -1 and +1 are singular points. Okay, and so why are these points singular point? Okay, please derive the function on these points and find something about, and you will say we have no derivation at this point. Okay, but please prove that. Okay, and let me continue with the reminder sentences about this critical points. Of course, if the function f of x, okay, is defined in an open interval, and okay, and as you see, this function is decreasing. Okay, and the x element of this point is 1 and this point is 0. X element of 0, 1 open interval. Okay, what can we say about it? We can say no maximum. Okay, no maximum points. Because of that, if you select this point is maximum point, okay, you can find any point which is larger than this point. Okay, and it goes on like that. And the same idea, okay, when you select, yes, this point is minimum point, okay, and we can say, but this point is less than this point, so it can be minimum point, so we can find any minimum points. Okay, and so that please attention for these open intervals. Okay, open intervals are problematic. Okay, for the critical points, and again okay, and this point is 2. Okay, and what can we say about that point? Okay, we can say if this is f of x function, okay, and for the, of course, x element of 0, 2 open interval, okay, and we can say no maximum and no minimum points. Okay, and if our graph, okay, like that, okay, and this point is +1, this point is 0.5. Okay, and what can we say about that? Okay, we can say, for example, for this point is local minimum point, okay, and for this point, local maximum, because of on this locality this point is maximum, and for this locality and this point is which is x equals 0, it's a local minima. But we have just found local maximum and local minimum points, but we can say no absolute maximums, and also no absolute minimum exists, okay? Because of, if you say yes, this point is local maxima, so I can say but same point is local minima, so which one is absolute maximum and which one is absolute minimum points, okay? So that you can say that. Okay, and after this example, okay, and they continue with the extreme of extreme values on open intervals, okay? Sorry, existence of extreme values on open intervals. I said the open intervals are critic, okay, and the problematic, I said, and now let's examine this type, okay, functions, okay, and let me firstly sketch the graph, okay, to understand this type extreme values, okay. Firstly this point is A and this point is L, okay, and this point is absolute maximum, okay, and this point is B, okay, and this is M, okay, and this point is U, and of course this point is f of u. Now listen me carefully please, and understand this theorem, because very important theorem it is. And if, okay, this function is f of x, of course, if f is continuous on a comma b open interval, and if limit x approaches to a from right hand side, okay, f of x equals to L, and limit x equals to b from left hand side, f of x equals to m. Okay, then the following will hold. Okay, I, or the first, if f of u is larger than L point and f of u is larger than M point, okay, for some u values which is element of this a comma b open interval, okay, which is the domain of f function, then f has, okay, an absolute maximum value on this open interval, okay, and the second one, if f of u is less than L and f of u is less than M for some u element of this domain, okay, then maybe we can change these points for the v point, okay, and this will be better, okay, f is f of v and the v element of a comma b open interval, then function has an absolute, okay, minimum value on a comma b, and a maybe minus infinity and b maybe plus infinity, okay, and the both L and M values maybe either plus infinity or minus infinity, okay, and now let's continue with example, okay. Y equals to f of x equals to x plus, okay, 4 over x, okay, has an absolute minimum value. Why? Because of limit x equals to, okay, and the 0 from right hand side, okay, and the f of x equals to, of course this function is defined on this interval, okay, domain of f, this, and it equals to, okay, plus infinity, which is L point, and the limit x equals to infinity f of x it equals to plus infinity, it equals to n. So we can find, okay, infinite numbers on which are less than L and M, because of L value and the M values are infinity, okay? So for example, at x equals 1, okay, which is f of x and also f of 1, which is 5, it is less than infinity, okay? So f of x at, we have just found only one point, okay, and we can find lots of points, we know that, has an absolute minimum, okay, on 0 comma infinity, okay, and to practice it, f prime of x, it equals to 1, okay, minus 4 over x square, okay, and it equals to x square minus 4 over x square, and it equals to 0, okay, we know that x minus 2 times x plus 2 equals to 0, and the x equals to minus n plus 2, these points are critical points, okay, and when you put these values, okay, and you will obtain f minus 2, for example, it will be minus 2 plus 4 over minus 2, it's equal to minus 4, okay, and when you put f2, okay, and you will obtain 2 plus, okay, 4 over 2, it equals to 4, okay. We can't select this value for the critical points because it's not on the domain, okay. It is not on domain, okay. So we must choose this one, okay, and this one is critical point of the function, okay.